Welcome to the Anti-Pattern Podcast, your ticket to the revolution in digital thread technologies. Please welcome, live from Mannheim, Germany, your hosts, Christian Muccio and Michael Fenning.
Hello and welcome to our second episode of this Anti-Pattern Podcast. Together with me in Mannheim, this is Christian, I'm Michael. And compared to the last time, one thing is new. And this is our beautiful new sign, the elevating pattern sign. It looks a little bit like being in an underground club, something like this. The bar needs to be here, right? And somewhere over there is the dance floor.
Yeah, at the moment we are operating in the underground. Right?
In the underground way, kind of, right? That's true.
Nobody knows us.
Nobody knows us yet. Yeah, that's true. Yeah, if I look at the window, it's not so much underground, right? We're exactly next to the Mannheim train station. So there is no underground in Mannheim. There's only regular trains running. So with that, directly to our topic. And today we want to talk about more technical things. We want to talk about the graph. So, and I guess we said it already last time, we are building our product on a graph database. And if you have a very quick look on my cup here, it says your product data is a graph and not a table. So, Christian, why is that?
Yeah, so if you are looking to your product data or what we have seen in our time as consultants, product data has always been a graph problem. Right. So in reality, it has always been a graph, but it was handled like a table.
Right.
In many cases. So if we are looking to a very prominent case in PLM, of course you find BOMs, and BOMs are at least trees, but you find always connections in between these, between some leaves, for example, because they depend on each other or whatever, and so you don't have a tree anymore, you have a net or a graph automatically.
A network of information, right?
Exactly.
And what I felt over the years is basically, if you look into the existing PLM solution, so to say, you actually see this is a graph problem. Right, but you know, the vendors and everybody in the market basically did in the past this. They used that graph problem and kind of put that into a SQL database, even if it was not a perfect fit.
Yeah, because it was state of the art at these times when most of the big solutions were invented, I guess. And speaking of solutions, if you're looking to different solutions on the market over the life cycle, you find at least 3 silos. You very often find the engineering silo with realistically dozens of sub-silos, the manufacturing silo, and the usage phase, or the operation silo, so to say. And each of these silos solved its problem partially. And for this partial solution, relational databases were sufficient in the past, at least.
Right.
And if you really want to connect these partial solutions in a horizontal way, our impression is that does not really work with RDBMS. And especially it's a performance problem in the end.
Right. And we come to that performance problem in a second. So you said horizontal integration. Right, meaning bringing together kind of all of the data models of the different tools, right? You said 3 silos, which is on a high level, correct, right? In reality, is of course way more tools that are used. But let's speak about the 3 silos, right? And if you want to bring that together in one, let's say, joint data model, in the past, people would have said, "Oh, it's actually easy, just bring it all in one system, all in one system, and everything will be integrated." Right? One monolith, right? And this is where I say basically that's BS, right? It's complete BS to say just because putting everything in one system, the integration issue is solved, right? Because this would require that the data models themselves are consistent. And speaking, Renaud, from experience, right? It's never the case, right? You look into that and you see, oh, guys, this particular line of business over here, they worked on something which is pretty much the same thing as the other guys, and they have their own data model, they have their own application, they may run on the same platform, right? But there's a lot of, let's say, semantical contradictions or semantical overlay, right? Overlap, right? This is existing. So the argument to say, just put everything in one system and the problem of integration is solved is not true, right? From our experience, from our belief, it's not true, right? And we need to do it or solve it in the future differently, and not just say put everything in one system, right? That's not the part. That's not the point. You have those different silos, and it's not that we say get rid of them, right? It's more like connect them in a more clever way, right? And talking about those line of businesses, right? There's one thing that I learned, I don't know, many years ago, Conway's Law. So Conway's Law basically means a good organization produces good IT systems, right? Because the patterns you see in the departments, in the groups, in the teams, those patterns and the communication between them is kind of the role model for the IT solutions that are picked, right? And it's not just the case that you say, okay, the organization that runs the software, right, follows that certain pattern. It's also true for software development companies, right? Because if they are not well organized in their development teams, you will see that in the software. And this is where we want to do also things a little different here. In other words, good organization leads to good architecture.
Exactly. And speaking of good architecture over the life cycle, it's my impression that we need some kind of persistence layer over the top. Because we have also seen different solutions of integrations between those silos, those three silos, and where linked data, for example,
Right.
Different tools trying to integrate these silos by one-to-one, one-to-n integrations, but that never really worked out. And maybe it's the case because this layer above these three silos can't be a relational database again.
Cannot just be yet another RDBMS.
Exactly.
Yeah, that's true. Yeah.
And that's the reason why we think, why we will try out, we will research in taking a graph database. And the interesting thing when you talk with people about graph databases is there is this big misconception of graph databases.
True.
Like,
Yep.
I pick some information together in a temporary graph database, in a temporary graph, then I put my analytics on it, and then I throw it away.
And then throw it away again. Yeah, that's our thesis. Is you can use, and others have proven that already, right? You can use a graph database to permanently persist data,
Exactly.
and also to run it in the business process, right?
Yeah. And next question that arises is which kind of graph database, which kind of graph are we using behind?
Right.
And very often you hear discussions about RDF-based graphs versus property graphs, for example,
Right.
or nowadays RDF star versus property graph. And the important thing for us, what we are researching in, is having not just a graph with nodes and edges. Right. The edges have to be also intelligent, have to have their own attributes, for example. And this is exactly what RDF is not capable of.
Not that easily, at least, right? And this is where you need RDF star for. This is what we're currently researching. And those relationships, they not just have a semantic, right? This would be, easy to say this relationship is this, semantic, and the other one is another one. They carry a lot of additional attributes, right? We want to do a lot of, contextual concepts. We want to implement a lot of contextual concepts, right?
Yeah.
One prominent example would be contextual release, right? Because a part is not just released by itself. A part is released in the context of an assembly, right? Something like this. And in other words, those, in German, Kantenattribute, those edge attributes, right?
Yeah.
They play a crucial role for us, and we need to find a very good way to put them into a graph database. Right. Talking about those relationships, maybe just one example. Why is this such a critical thing for us, right? the amount of data. And that maybe serves also as an explanation why it has not been done before or was not, possible to do it. And that is, if you really think about it, bringing together those three silos, engineering, manufacturing, operation, and maintenance, and you think about if you serialize, right, down to the digital twin level, down to the instance level of things. Just imagine you're a car manufacturer. A car has roughly 30,000 parts, right? And you say, I produce 1 million cars a year, right? And if I want to have the exact structures of everything, right, implemented or, persisted, 30,000 times 1 million is 30 billion, right?
And that's an enormous number.
It's enormous.
It's an enormous number, which needs really high performance.
Right.
And this is exactly why we think that we, on the one hand, need the graph database.
Right.
In the first place. Afterwards, we would have to have a look on regular databases, regular graph databases, or even in-memory databases.
Right. As a second step, so to say.
As a second step, exactly. And if you have it in memory, you also have to take your analytics on it. That's clear. Or you have to have high performance to hop from one node to the other and get your answer to your question. And therefore, we will also have a look if the usage of GPUs might be an advantage.
Yeah, so this is what we're currently researching also in the benchmark that we're currently running, right? We have not yet decided what kind of graph database is this going to be. We know it needs to be a graph database. But let me ask you this then. Is it only one graph database where we are going to persist in, or is there,
No, definitely not. So I think we will go a polyglot persistence way. And we will choose the right database for the right problem.
Right.
So basically, if you have a time series problem, you have sensor data in your operations phase,
right,
you want to track, you don't write that in a database, in a graph database, and you don't write that in a table anymore. Nowadays, you take a time series database for it.
Right. But the tool itself, or our platform or software platform, needs to be capable of, managing what kind of data of the graph is persisted in the graph database, is persisted in, you said time series, key value store, what have you, right?
Vector databases, whatever is on
whatever it is, right? So, and this is what we need the modeling engine for in the database. And this is going to be, we are 100% sure, I guess, that this is going to be C++, also because of performance reasons, right? But the modeling engine does something in addition, and that is flexibility, right? It gives the possibility to run it kind of in an low-code, no-code way, right? So there is a standard meta model that we deliver, right? That we build, that we implement on. And then there is a layer above it where customers and us as software developers, ourselves as well, are able to come up with our own specific data models for specific domains, right? For example, there will be, I'm pretty sure about that, some kind of a BOM solution, right? We call that BOM app or whatever we're going to call it. And this is based on the meta model, right? And the way it is developed is completely the same if we do it or if a customer does it in a customized way, right? So this is where the modeling engine plays a huge role, and flexibility itself, to me, has always been crucial. I would say the most important thing about PLM systems. And I guess I was never part of a majority vote here, but not really. But flexibility and extensibility of a PLM system is crucial because it's not so easy as in other domains, right? If you look into, I don't know, the invoice process of a car manufacturer compared to a medical device manufacturer, potentially the same, right? Or at least to 90% the same. But how they develop, how they manufacture, and how they operate their technical systems, no way to compare them. It's not even possible to compare a car manufacturer called, I don't know, with another one. Even if they're both from Germany, right? You can't compare how they actually operate. So there needs to be a lot of flexibility. And this is why I say, I want to talk about the fairy tale of standard software, which, was around for so long and which is actually in reality, never the case. And that is software is sold as, buy it, get it out of the shelf, install it, and it's working. You can buy your business process, right? This is kind of the story.
Tale.
That's a complete fairy tale. This is the one extreme. The other extreme is there's a toolbox, right? We're just delivering a little piece of software above a database, and go for it. You can build whatever you want. Both approaches, standard software and toolbox, are basically nothing for the future. They are proven to be wrong, and you need to find a good compromise between the two.
Yeah. I think this is key. The good compromise, and the modeling engine will play an important role in this case.
Right.
And one thing we would like to discuss in future is schemalessness.
Schemalessness.
Is this our English word? Schemalessness.
Oh, write that in the comments, please.
Yeah, native speakers, please feel free. Is it an advantage to be schemaless if you are using a graph database?
Right.
Does it provide more flexibility, or does it provide also different problems in the runtime?
Right. I mean, we have been talking about this, right? Imagine you're schemaless. That means you can add data without following a predefined schema, right? This is where the schemaless is coming from, right? That means, you could allow to store data, right, on the persistence layer that is not following any schema. Question is, at some point, you may find out, actually 80% of our people are actually storing the same stuff that has no schema, so to say, that it's, following. And can you then kind of create a schema from that unstructured data and make it structured, right?
Yeah.
Is that a process that, makes sense to engineers out there?
And that's really hard to say because it was never there. So I don't know any PLM, digital thread system, whatever, which works schemaless and allows even to store non-schema data.
Right.
So nobody knows that.
Yeah. So this is a research question for us, right? This is something we want to try out and find out if that actually makes sense, right? Because we now have that opportunity to do that in a graph database, right? And this is why we think it may make sense. In the past, if people found out I have more data that is not yet in the model, they would go to the admin, right, and say, "Please, admin, can you add something to what entity?"
We all know how well this process was running.
Depending on the tool that was used, some tools supported that better, others did not really, right? So yeah, that's the thing. But let's investigate it, of course, and we keep you guys updated on what we find out. So flexibility is at the core in our strong belief of any PLM solution in the future, and definitely in our DTS, right, in our digital thread system. And there will be more principles than just flexibility. One spoiler: openness, of course, right?
Yes.
Openness is really, really important. And that can, for some vendors in the future, even be a legal issue, right? Because there is a lot of regulation about data in the moment, right? And openness is one of the things that are really, really pushed for good reasons, right? And but there are others, right? It's not just openness then and flexibility. There will be more.
We already talked about performance.
Yeah, and we already talked about performance. So this could be something for the next episode when we dig a little deeper into our thinking for a digital thread platform. And with that being said, anything to mention? Anything to add?
I think that's enough for today.
That's enough for today. With that being said, thank you very much for your attendance and your interest. Please follow, subscribe, leave a comment if you like what you heard, and see you next time.
See you next time. Bye, folks.
Yep. Bye-bye.